So in this video we'll be talking about fusion, and the definition of fusion is when small nuclei combine. So comparing fission to fusion, fission is a much more favourable energy source based on the amount of energy you need to make the reaction happen is actually a lot less compared to fusion. But fusion is actually happening in the sun, and it generates all the energy that we get from the sun. So as human beings, we get the vast majority of our energy from plants, pretty much all of it. So whether we eat plants or we eat animals that have eaten plants, plants actually trap the energy from the sun, convert it into food, so that's how we get off most of our food, and therefore most of our energy from the sun. So the energy that the sun produces is based on nuclear fusion, and it actually involves the conversion of hydrogen into helium. So hydrogen is the smallest nuclei. It's got one proton in this isotope. There are other isotopes of hydrogen, but that's the one that's involved in the conversion of conversion into helium. So this conversion from hydrogen to helium is happening in the sun, and it's generating the energy that plants then trap to give us our energy. But as a power source, like nuclear power, it's not used, and we'll see that in a second. It actually takes a really high temperature to make this reaction happen, so it's not really feasible. But fission, on the other hand, is, because you actually don't need that many extreme reaction conditions to make it happen. So anyway, let's go back and look at fusion in the terms of energy. So in the sun, the amount of energy that's produced in 1 second is 3.8 times 10 to the power of 26 joules. Joules is an energy unit that we haven't really talked about in class, but that's what we use. So at 1 second you get a huge amount of energy produced. Compare that to something that we use, like a gallon of gasoline. You need 3 times 10 to the power of 18 gallons of gasoline to produce the same amount of energy in 1 second. This amount would fill Lake Washington multiple times, many times. So a huge amount of gasoline would need to be burned to produce the same amount of energy that we get from the sun in 1 second. And what's actually happening in the sun is a huge quantity of hydrogen is being converted into a huge amount of helium, and then there's a lot of energy given out as a result. And again, thinking about nuclei and having a certain amount of energy, because a certain amount of energy is needed to keep the nuclei together. So if there's a change in the nuclei, that usually results in a huge amount of energy being given out. Say, for example, with fission and also fusion, if you fuse two nuclei together, you lower the potential energy, so then that energy is then given out, or as something, usually light, heat in the case of the sun. So where are we? So there isn't a huge amount to say about fusion, but this is what's happening chemically. So we take one atom of hydrogen, combine it with another one, and we get this version of hydrogen, which has 2 neutrons but 1 proton. And so what also is produced is an antimatter electron, or a positron, so that's produced as well. So that then off it goes, and it reacts with something else almost instantaneously. So then we take this isotope of hydrogen, it combines with another atom of hydrogen, produces a helium isotope. You'll notice that it's 3 and 2, not 4 and 2. So this version is actually very unstable, but as all these isotopes are produced, they actually combine together to produce a stable version of helium, for a mass number of 4, atomic number of 2. And what's also produced in this reaction is another pair of hydrogens, which then go on to fuse together to make start the reaction again. So that's the nuclear reactions of hydrogen being converted into helium. Happens in 3 steps rather than just 1, but can't win them all. And so this reaction requires this temperature, which is 40 million degrees Celsius, which is very, very difficult to maintain on this planet. But fortunately, the heat and energy from the sun is driving this reaction. So on Earth, we can very economically sustain this temperature for this to be a viable power source. So, but luckily, the sun does this without much thought. Not that the sun thinks, but you know what I mean. Anyway, so you've got a huge amount of energy needed to start the reaction, but once the reaction happens, even more energy is given out, and that's energy that we experience from heat and then light as well. And so then plants trap all that light energy, or a lot of that light energy, converted into food that we eat, or other animals eat, and then we eat those animals. So a lot to be said for fusion. It's very, very important. So, and that's it.